Hello and welcome to Corrosion Engineering Electricity Basic Knowledge Training Course, part number 1. This course intended to provide and refresh the essential electrical knowledge and the skills every corrosion personnel, including corrosion engineers and technicians, CV technicians, and chemical laboratory personnel should have. This training course will be imparted. This course is part number 1. By the end of this course, you will be able to solve electrical circuits, finding the missing electrical resistance, electrical current, and voltage drop. In addition, you should be able to understand what is meant by electrical current, voltage, and resistance. Example of the electrical circuit you will be able to solve by the end of this course. Here we have a group of electrical resistance connected in different ways, and 2 sources of electrical voltage. So by the end of this course, we will be able to calculate the current passing through any of these electrical resistance. Also, we will be able to solve the equivalent and find the electrical resistance equivalent between any 2 points. So this course, it was presented by LinkedRings Ltd. LinkedRings is Asset Integrity Engineering Consultant, UK-based company. Our website address is www.linkedrings.com. Our email is info@linkedrings.com. We are fully registered company in UK, and we are providing different kind of service, including free training, paid training, free consultation to oil and gas companies, oil and gas and petrochemical companies, also paid consultation. So please visit our website to know about the new coming courses. So as a matter of fact, this course was provided on the 10th of October as virtual instructor lead training course. Virtual instructor lead training course, it means the participants of this course will be in a meeting, virtual meeting with the instructor, and we had given the course online, live, where the participants are able to interact, and the participants will be given questions where they will answer if they wish to do so, to participate. So this is a virtual instructor lead training course. So we hope that we can see you in upcoming courses. I may forget to mention that this course is provided to you by Asset Integrity and Corrosion Principal Engineer Osama Nakhla, which is happen to be myself. So welcome to this course. Please read the terms and condition policy for this course and understand and agree before proceeding further. Take your time and read it, please. Course index. This course has been divided into 4 chapters, chapter 1, 2, 3, and 4. So in chapter 1, we are going to explore some basic terminologies and definitions. And in chapter number 2, we are going to present the different kind of electrical circuits. In chapter number 3, we are going to explore the basic electrical laws. And in chapter number 4, we are going to implement the knowledge which we learned in chapter 1, 2, and 3 for solving some examples of electrical circuits. So, as we know, corrosion is a process that converts a substance into a more chemically stable form. Also, it's described as the destruction of material by chemical or electrochemical reaction with the environment. In course number 2, sorry, in part number 2 of this course, we will be talking much more about what is corrosion and why it's happening, how it's happening in more details in part number 2 of this training course. So we hope to see you. So example of the very famous form of corrosion, which we are familiar with, is the rust. Ferrous ions forms at the anodic area, and hydrogen releases at the cathodic area in local cell of iron surface. So if we are having a local iron surface, means an iron surface exposed to the atmosphere, parts of this surface is more active than other parts, more active in the sense of it will interact and make some form of reaction with the environment. The active parts, we name it as anodes, and the less active parts, we name it cathodes. On the anodic area, which is the more active parts, ferrous ions, Fe2+, will form. And on the less active parts, which we call it cathode, the hydrogen will be released. Again, more explanation of this will be in the following parts of this training course. Here we can see that this is a typical schematic diagram for cathodic protection, impressed current cathodic protection, in where the protected steel, like protected steel in the underground, is receiving a current, we call it protective current, from the anodes, and typically the protected structure will be connected to the negative side of the rectifier, and the anodes will be connected to the positive side of the rectifier. So as you can see here, while we are talking about corrosion, we are talking about ions, we are talking about ions. Also, electrical instruments are used in some corrosion monitoring and testing, and with no doubt in CD survey, cathodic protection survey. Cathodic protection activity requires truly understanding of electrical circuit. In this chapter, some of the most used electrical basic concepts will be discussed. So what is atoms? Atoms is the smallest unit of matter that forms a chemical element. Every atom is composed of nucleus on the center of the atom and one or more electrons. The electrons are bonded to the nucleus. Nucleus is made of one or more proton, one or more neutrons, excluding the most variety of hydrogen, which has no neutrons. More than 99.9% of the atom mass is in the nucleus. In another word, the electron mass is negligible to the, very much negligible to the, compared to the nucleus mass. The protons having a positive electrical charge, the neutrons have no electrical charge, it's neutral, neutron, the name suggesting. Electrons have a negative electrical charge. Electrons are playing part for forming chemical bonds between atoms, ions, or nucleus. An atom with neutral charge, it means the number of the electrons are equal to the number of the protons. Example, Fe is a neutral atom of iron. Positive ion, in which the atom has been stripped one or more electrons. In other words, the number of the protons are more than the number of electrons. Example of the positive ions are Fe2+, which we call it ferrous ion. It is an atom that has been stripped of 2 electrons. That's why it's +2. Another example is Fe3, which we call it ferric ions. In this condition, the atom has been stripped of 3 electrons. Negative ions is an atom that have 1 or more electrons, such as chloride -1. So have 1 or more electrons more than the protons. Chloride ions may also be created when a compound such as HCl, hydrogen chloride, is dissolved in water. Coulomb is SI unit of charge, and 1 coulomb is equal to 6.241 times 10 power 18 electronic charge. So a group of electronic charge with the number of 6.241 times 10 power 18 equal to 1 coulomb. Joule is an energy unit. We symbol it with the G. Is an SI unit. SI is the International System of Units. Is equal to the energy transferred to or the work done on an object when a force of 1 Newton acts on that object in the direction of the force motion. So this is an object, and this is a force of 1 Newton. When this force is acting in the object in the direction of the motion for 1 meter, then we can call this one is 1 joule. So 1 joule is equal to 1 Newton meter. Also, the joule is energy dissipated when a current of 1 ampere is passing through a resistance of 1 ohm for a time of 1 second. Voltage. Voltage, potential, electrical potential, difference electrical pressure or electrical tension, all are terms referring to the same thing, referring to the electromotive force or the difference in the electrical potential between 2 points. We can simulate it like the difference in the water level, for example. Okay, also defined as the work required to move 1 unit of a charge, or the force that puts the charge in motion. So the work required to move 1 unit of charge, coulomb, is voltage. In SI unit, SI International System of Units, voltage is work, means energy, voltage. So it is joule. So the voltage is the joule per coulomb. Work required to move 1 unit of a charge, joule per coulomb. The symbol of the voltage are, normally we use 3 symbols, EMF and capital E and V. So EMF is electromotive force. E is voltage raise. So this is voltage raise, then we refer it to capital E, such as when we have battery or pipe destroy potential. V, we refer it to when we have a voltage drop, like we have a resistance and there is a voltage drop because of this across this resistance. So we use the term V. So this is just for us to remember about the unit conversions. So 1000 volt equal to 1 kilovolt. Okay, 1 volt, how many millivolts? Equal to 1000 millivolts. Millivolts here, we can write it as millivolts or small mV. So mV means millivolt. Capital M different from small m. This is small m, so millivolt. 1 volt equal to how many microvolts? Equal to 1 million microvolts. 1 million means 10 power 6 microvolts. This is the symbol for the micro. 1 millivolt equal to how many microvolts? Equal to 1000. So this is the way how we write these units by using the handwriting. I just repeated what I wrote to you in the a second ago in order to show you how this to be written by using the handwriting. This is how to write microvolt. This is how to write millivolt. Okay, let's get some more example on unit conversion. So 0.025 volts. How many millivolts? Okay, so we multiply by 1000. So equal to 25 millivolts. How many microvolts? Again, multiply by 1000. So equal to 25,000 microvolts. 1250 millivolts. How many volts? Okay, we divide by 1000. So it is 1.25 volts. Okay, this 110,002 microvolts. How many millivolts? We divide by 1000. So it is 110.002 millivolts. How many volts? Again, we divide by 1000. What is current? Current is the rate of flow of electrical charge past a point or a conductor. Also, current is a flow of a charge along a conducting path. In SI unit, the current is measured in amperes. We symbol it by AMP, which is the flow of electrical charge at a rate of 1 coulomb per second. So current is 1 coulomb per second, equal to 1 amp. 1 amp is 1 coulomb per second. As we mentioned, the coulomb C is the SI unit of electrical charge, and 1 coulomb equal to the unit charge carried by 6.241 times 10 power 18 electron charges. Symbol for the current, I stands for the current, regardless of any unit used, milliampere or ampere. We say the current I equal to some values, and we can say milliampere, kiloampere, ampere. Okay, ampere or amps, all are the same. We can write amps, we can write capital A, we can write ampere. Milli, small m, capital A, so milliamp, milliampere. Microamp, microamperes. 1 ampere equal to 1000 milliamperes, so equal to 1000 milliamperes. 1 ampere equal to 1 million 10 power 6 microampere, and 1 milliampere equal to 1000 microampere. (1,250 milliamps equal to how many amps? We divide by 1000, so 1.250. 300 amps equal to how many milliamps? So we times 1000, so 300,000. 300 milliamps equal to how many microamps? Again, we multiply by 1000, so 300,000 microamps. So what is electrical resistance? Electrical resistance of an object is a measure of its opposition to the flow of electrical current or its opposition to the flow of charges. SI unit of electrical resistance is ohm. 1 ohm is the resistance of a conductor when a voltage of 1 volt produces a current 1 amp along the conductor. So if we apply 1 voltage and this will produce 1 amp along the conductor, it means the resistance of this conductor is 1 ohm. The symbol of the electrical resistance are R, stands for resistance. Ohm is SI unit for the electrical resistance. Here we are having also the 1 ohm equal to 1000 milliohms. 1 ohm equal to 1 million micro ohms. 1 ohm equal to 1 kilo, 1000, sorry, 1000 ohm equal to 1 kilo ohm. 1000 ohm equal to 1 kilo ohm. 1000 kilo ohm equal to 1 mega ohms. 1 mega ohm. You notice here capital M. So capital M, it means mega. Small m means milli. They are different. They are not. Electrical resistivity. Electrical resistivity is a fundamental property of a material that quantifies how strongly it resists electrical current. Resistivity is an intrinsic property. Intrinsic property means it's a natural property. Resistivity may be defined as the electrical resistance between two parallel faces of 1 unit length couple. So 1 unit length couple, the electrical resistance between side A and side B is defined as the resistivity. We say 1 unit length because it can be, for example, 1 centimeter or 1 meter. If it is 1 centimeter, then the electrical resistivity will be ohm centimeter. If it is 1 meter, then the electrical resistivity will be ohm meters. Resistivity of a material, for example, such as pure copper rod, is fixed value for any parts made of or cut off that rod. It does not depend on the shape of the cutting. It is intrinsic property, natural property. Resistivity, this is a symbol for resistivity, rho, equal to resistance times the cross-sectional area divided by the length. If you notice here, the unit for the area is square length unit divided by length unit. So that's why finally it will be ohm meter or ohm centimeters. If you don't understand this, it's fine. So resistance R is in ohms, area is in square centimeters, and length in is in centimeters. All the units which we are using here should be consistent. For example, we're talking here about the area and the length. Either we use square centimeter and centimeter, or we use square meter and meters, for example. Okay. And then the resistivity units will follow. Either will be ohm centimeter or ohm meters. Electrical conductivity. Electrical conductivity is a fundamental property of a material that quantifies how strongly it conducts electrical current. Electrical conductivity, yes, you're right, is the inverse of resistivity. Electrical conductivity has two symbols, sigma and MHO, mho, is the reverse of ohm. Ohm is OHM, mho is MHO, and the shape is reverse. Sigma also, its value will be the reverse of the resistivity. So it is the length divided by the resistance times the cross-sectional area. Sigma, electrical conductivity in Siemens per meter. R is the resistance in ohm, the area in cross-sectional area in square meter, and the length in meters. So all the units used to calculate the electrical resistance of any shape, any object, should be consistent. For example, if we use centimeter, we use centimeter. If we use meter, we use meters. For example, if the rectangular shape with cross-sectional area as a rectangle, the cross-sectional area will be the length times the width, A times B. If it is cylindrical shape like a wire, the area, and it has a diameter d, so the area will be pi divided by 4d squared. This law must be memorized, the area for a circle, or you can use pi r squared. Pi r squared is same as pi divided by 4d squared. Pi is equal to 3.14. Let's explore some of the electrical resistivity of some common material we see in our life. Metals in general are good conductor, meaning it has smaller electrical resistivity. For example, silver is have electrical resistivity of 1.6 times 10 power minus 6 ohm centimeter. 10 power minus 6, it means 1 part of a million. So this value divided by million. This is the meaning of 10 power minus 6. So this add for the some materials at 20 degrees Celsius, yes, there is a change with temperature out of the scope of this course. So here we will see the electrical resistivity in ohm centimeter. Here we will see the electrical conductivity in sigma per centimeter. Silver is good conductive, and copper is good conductive. So they are having electrical resistivity very small of almost 1.6 times 10 power minus 6. While the electrical conductivity will be high, so it is around 6 times 10 power 5. Yes, the silver is slightly better conductor than the copper. The rubber is insulator. That's why it has very high amount of electrical resistivity, 10 power 15. And it has small conductivity of 10 minus power 16. By the way, the rubber is different types, and it depends on the density, if it is a high density, low density, medium density, and some other factors. So this is example of the rubber types. We notice that the resistance equal to the resistivity times the length divided by the area. What that means? If the length is increased, the electrical resistance will increase. If the area, cross-sectional area, increase, the electrical resistance will decrease. This big, the area, then the resistance will be smaller. The length is bigger, the resistance will become larger. So longer wire have more resistance than smaller length wire. Thick wire will have less resistance than thin wire. Let's review some math here. What is 10 power 1? 10 power 1. 10 power 1 means 10. Simple. 10 power 2, it means 100. It means 10 times 10, 2 times. 10 power 3, it means 10 times itself or 3 times. So 10 times 10 times 10, so it means 1,000. 10 power 4, it means 10 times itself for 4 times. So 10 times 10 times 10 times 10, so 10,000. Okay, so on. 10 minus 1, meaning what? 1 divided by 10 equal to 0.1. 10 power minus 2, it means 1 divided by 100. So this value. 10 power minus 3, it means 1 divided by 1,000. So 0.001, and so on. So as we mentioned, just to refresh it again, if we have a circle, cross-section area of a circle with diameter d, radius is r, so d is equal to 2r. the diameter equal to double the radius. The area of a circle is pi divided by 4d squared, where pi equal to 3.14. Or the area of the circle equal to pi times r squared. Example, if r equal to 5 centimeters, the area in square centimeters will be equal to 3.14 times r squared. So 3.14 times 5 millimeter, we convert it into centimeters. So 5 millimeters equal to 0.5 centimeters, so 0.5 square. So equal to 3.14 times 0.25 equal to this value, 0.785 square centimeters. To convert from, in some our life examples or exam problems, exam questions, we may find the unit of the resistivity not in ohm centimeter, it is in ohm meters. So to convert from ohm meters to ohm centimeters, multiply by 100. For example, the copper electrical resistivity, 1.68 times 10 power minus 8 ohm meters. That is the same as 1.68 times 10 power minus 6. So the base value is the same. The 10 will be times 100. So multiplied by 100. So multiplied by 100 means this minus 8 will be, you will add to 8 plus 2. So minus 8 plus 2 is minus 6. Rectangular shape. What will be the area? If the shape is triangle, what will be the area? So for rectangular shape, the area is the length times the width. For triangle, it is the base times the height divided by 2. This need to be memorized. What about if I have hollow conductor? Hollow conductor of outer radius R1, inner radius R2. So in this condition, we need to know what is the cross-sectional area of this shaded area. So the cross-sectional area of this shaded area will be the area of the circle R1 minus the area of the circle R2. So it will be equal to pi R1 square minus pi R2 square. Pi will be taken as a common. So R1 square minus R2 square. Some of the common mistakes some people could do is to say it is pi multiplication of R1 minus R2. This is wrong, and multi-question examples, they will choose for you one of the answer like that. So if you do it that way, you will choose the wrong answer. So it is different. This is the value for the cross-sectional area. As we mentioned, the larger the cross-sectional area of a conductor, the smaller the electrical resistance. The longer the length of the conductor, the larger the electrical resistance. The larger the electrical resistivity of a conductor, the larger the electrical resistance. Electrical resistivity of soil and water may highly impact the cathodic protection requirements. It means how much current is required to protect the structure. Electrical resistivity vary greatly. It could be, for example, 20 ohm centimeters for seawater. This is a good conductor. To say very high value of 500,000 ohm centimeters for dry sand. Note that the corrosion technician, in particular the CP technician, will be involved in taking various electrical measurements, such as structure to soil potential measurements and voltage drop across shunts in order to calculate the passing current. Electrical symbols. Electrical symbols are important chart we should be aware about in order to understand the electrical circuit when we see an electrical circuit. So the resistor or resistance having this kind of shape. If we have an arrow, it means it's a variable resistor. It means the value can be changed. Transformer having this shape, which it means two coils. Transformer is to change the input voltage to be different from the output voltage. Batteries in series, it will be having this shape. Single battery will be just like that. Diode will be in this shape. Diode will allow the electricity to go in one side, does not allow it to go from the other side. So from here, from the left, the current can pass from the left to the right, but it cannot pass from this side to the other side because of this one. This one means blocking. This is the ground connection symbol. Rectifier. Rectifier having this kind of shape, example for it, which is consists of 4 diodes. This symbol, it means these wires are connected in this dot. If the wire are crossing but not touching, not connecting, it will be having this shape. This shape means a switch. Transformer could have this shape. Impressed current cathodic protection could have this shape, whereas and one terminal will be negative, one will be positive. Okay. What is alternative current? Alternative current will have this symbol in a circle, and it means the voltage is changing from in the cycle from positive value to a negative value, and then again return to a positive value. It means this terminal will be sometimes negative and sometimes positive. This side will be sometimes negative, sometimes positive. This is called alternative current. Okay, how many times will it change? For example, for most housing, it is 50 hertz. 50 hertz, it means 50 times per second will be in one second. We'll have the wave of 50 waves. So 50 waves in 1 second. From this point, going through all this line up to here, this is called one wave. So 50 hertz means we will have this much 50 times, repeating in 1 second. Direct current, it means there is always one side is positive, another side is negative, and we can have the current direction. And direct current could be straight or could be vibrating, but still it's always positive side or negative side, the voltage. So this is called DC current. What will happen if we are having AC alternating current and we will add to the circuit one diode? So if there is no diode, like this circuit, this is a source of AC alternating current passing through the resistance or load. So the wave will be having this kind of shape. This vertical is representing the voltage, and this horizontal representing the time in milliseconds. What will happen if I add the diode here? If I add the diode, so when this one is positive, the current will go in this direction, and it will continue the cycle. When it's reverse, this become negative, the current cannot pass. So what will happen? When it's positive, the current is passing, but when it's negative, there is no current. So it's positive. When this side is positive, the current will go in this way. The current cannot go here, so the current will go in this way. So this is the output of the rectifier. So it's positive. Okay. the current cannot go in this way. So this is a secondary circuit or half wave. We call it half wave. So this is the half wave. What will happen if I have this kind of shape? So here we are having 4 diodes, and the AC source is connected in this way. It will go to the load, and it will return to the other side here. So these 2 points are the output circuit, and this is positive. Okay, what will happen during the other half wave or half wave? During the other half wave, where this side is negative, this side is positive. So this side is negative means what? The current is going through this here. Okay, and this side is positive, it means the current will go from this way. So this way, the current cannot go here, so the current will go here. Oh, so this is again positive. So it's always this side is positive, always it's positive. And again, the current will go on the secondary cycle, and it will return to this side, and it will continue the circuit through this way. That's why we call it full wave rectifier or 4 diode rectifier. This is an example of electrical circuit in which we have multiple batteries connected, and it will give us some kind of amperes of 12 milliamperes, and the resistance is 1000 ohm. So in the remaining part of this course, we will use hand sketches like the one which you have saw now for making all the circuits. The reason is that simplifying things, as this course is intended for training and is not for design of electrical circuits, hand drawing is satisfying the purpose of this course for training. So we are in chapter 2, electrical circuit type. This is a short chapter. This is how we draw the circuit. This is the electrical source, the current, switch, the load, and this is the second load, and this is the current again returning. This is called series electrical circuit because the loads are connected in series. Example, if I can put in R1 could be a light bulb, R2 could be electrical motor. Now, this is another example of another circuit in where the 2 loads are connected in parallel. So this is, we call it parallel circuit. In our house, all the loads are connected in parallel. Why? Because if they are connected in series like that, if there is an outage here in the light bulb, like the light bulb is damaged, the motor will not run, for example. And there is another reason also. Now we are in chapter 3, electrical circuit types and basic electrical laws. So Ohm law stating that E or V, electrical voltage source, or V, electrical voltage drop, equal to the current times the resistance. So V equal to IR. From this, we can extract that R equal to V divided by I, or I equal to V divided by R. This is a very important law, and we must know it very good. The unit must be consistent. For example, when we use milliampere and millivolt, the resistance will be in ohm. For example, R equal to 1000 ohm and E equal to 12 volts. Calculate the current. So V equal to IR. That means I equal to V divided by R. So I equal to 12 volts divided by 1000 ohm equal to 0.12 ampere, which is 12 milliamperes. Example, if the resistance equal to 1 mega ohm, and the E equal to 12 volts, calculate the current. So we notice here the units are not consistent. We have here mega ohm, mega, and we have here volts. So we have to take this one into consideration. So the V equal to IR, so I equal to V divided by R. So V 12 volts, and how much the R? 1 mega, it means 1 times 10 power 6 ohms. So it means the current will equal to 12 times 10 minus 6 amperes, which is 12 microamperes. As we discussed earlier, energy is a property that must be transferred to an object to perform work or to heat the object. So energy is the property that must be transferred to an object to perform work or heat the object. Example, for heating 1 liter of water, an amount of energy required shall be spent to heat the water. Energy has different forms. Some of the common forms of energy includes kinetic energy of a moving object, thermal energy, chemical energy, and electrical energy. Very well known famous law of energy stating that the law of conservation, the law of conservation of energy states that energy can be converted in form but not created or destroyed. Joule, as we mentioned earlier, is SI unit is equal to the energy transferred to or work done on an object when a force of 1 Newton, when a force of 1 Newton acts on that object in the direction of the force motion through a distance of 1 meter. So Joule equal to 1 Joule equal to 1 Newton meter or Nm. The Joule also is defined as the energy dissipated as heat when electrical current 1 ampere passing through a resistance of 1 ohm for 1 second. I must specify here the time, 1 second. What is power? Power is the amount of energy transferred or converted per unit time. In SI unit, the unit of power is the watt, equal to 1 joule per second. So the power in watt equal to E times I, or the power equal to V times I. So the power equal to the voltage times the electrical current. When mixing Ohm's law and power law, so V divided by R is equal to the current. So the power equal to V times I, it means V times V divided by R. Here I replaced the I by V divided by R. So also the power equal to, if I remove the E here, equal to IR. So the power equal to IR times I equal to I square R. So the power could be VI or I square R or V square divided by R. All of this is just two laws only to remember. V equal to IR and power V times I. From these two laws, we can extract and find many other laws. What is Kirchhoff law? Kirchhoff law, let's study this circuit where I have two electrical sources, E1 and E2, and I have two loads or two resistance connected in series, R1 and R2. So the current passing by through the resistance, I times R1, will equal to the voltage drop across this resistance, Ohm law, correct? V equal to IR1. This is V1. Okay, the voltage drop across the second resistance will equal to I times R2. So V2 equal to I times R2. Okay. The summation of voltage source E1 plus E2 equal to the voltage drop V1 plus V2. So the sum of the source voltage across any closed loop of a series circuit. In this circuit, the sum is E1 plus E2 is equal to the voltage drop across the resistance in the loop. So this is a closed loop series electrical circuit. The sum of source of voltage. So this is the source of the voltage. What are they? E1 plus E2 is equal to the voltage drop across the resistance in the load. So it is equal to V1 plus V2. And here it comes Kirchhoff law. Again, I will read it one more time. The sum of the source voltage around any closed loop of a series circuit is equal to the voltage drop across the resistance in the load. So this law, Kirchhoff law, is known to be series circuit law. Series circuit law. So it has two names, Kirchhoff law or series circuit law. Current law. We are seeing now a parallel electrical circuit, R1 and R2 resistances connected in parallel with these two resistors are connected in parallel, and the power source are E1 and E2. So if we apply Kirchhoff law around this closed loop circuit, the voltage source E1 plus E2 equal to voltage source equal to the voltage drop. So the voltage drop will be I1 times R1, as I am looking for this closed loop electrical circuit. What will happen when I look to the other electrical circuit here, the other one, this electrical circuit? So the same thing, electrical voltage source E1 plus E2 equal to the voltage drop, which is I2 R2. So what that means? That means I1 R1 equal to I2 R2 equal to E1 plus E2. Here I am having at this dot the current input to this point is I3. The current output is I1 and I2 here. The current is the flow rate of electrical charge. I3 must equal to I1 plus I2. Current is the rate of flow of electrical charges past a point or a conductor. Also, the current is the flow of a charge along conducting path. This is the definition of the current. So the current law is the sum of the current, which is the rate of electrical charge entering any point, is equal to the sum of the current leaves that point. This is called current law, and it is specified for parallel circuit. So sometimes we call it current law, sometimes we call it parallel circuit law. Anyway, it's specified for parallel circuit. So let's take another example here. Here I have 3 resistors connected in parallel, R1, R2, and R3. Let's talk the yellow color closed loop. Yellow color closed loop, we call, how we name it? We call it D, E, F, G, D. D, E, F, G, D. Where we start, we must end. So apply Kirchhoff law. What are the input voltage here? The input voltage here, or voltage source here, are 0. Okay, so 0 equal to the voltage drop. What are the voltage drop? So 0 equal to R3 I4 minus R2 I2. So it means I3 times I4 equal to R2 times I2. This is equation number 1. Now we will take the green color closed loop circuit, C, D, G, H, C. Same thing. This is the direction of the current we're assuming. So the voltage source are 0. So 0 equal to I2 times R2. Then I work with the circuit. I am opposite here. So minus I1 R1. So what that means? That means I2 R2 equal to I1 R1. I equal this equation number 2. Now we took the third closed loop circuit, gray color circuit, P, C, H, A, P. So the way I am pronouncing the circuit is identifying where is the assumed current direction, positive current. So the input voltage is E1 plus E2, because why they are plus, no negative? Because they are in the same direction with the assumed current. So E1 plus E2, this is the source current, equal to voltage drop, which is I1 R1. This is equation number 3. Let's take this circuit where we have 3 resistances, the same previous circuit, and study it more. So from the equation 1 and 2 and 3, we come to the point that E1 plus E2 equal to I1 times R2, which is equal to I2 times R2, which is equal to I4 times I3. The current law tells us the sum of the current rate, the sum of the current, which is the rate of electrical charge, entering any point, equal to the sum of the current leaves that point. So let's take each point one by one and see what that means. Let's apply the current law. So here, this yellow color point, the current leaving is I2 and I4. So this current leaving I2 and I4. The current entering is here. How much is current entering? It will be equal to I2 plus I4. Let's take another point, which is this red color point, yellow color point. So the other point here, let's apply also the current law. So this point having current entering is I3, current leaving is I1, and another current leaving is I2 plus I4. So what that means? The current entering equal to the current leaving. So what that means? Current entering is I3, current leaving equal to I1 plus I2 plus I4. Current entering equal to the current leaving, that point. Let's take another point. this point. I4 is entering, I2 is entering. So how much is the current leaving? Yes, it will be equal to I2 plus I4, correct? Let's take another point. This point here, this point. What is the current entering? I2 plus I4. And what about this branch? I1. So what will be the current here? The current will be here I1 plus I2 plus I4. Oh, is this the same current as I3? Actually, yes. So what that means? I3 equal to I1 plus I2 plus I4, confirming this equation. This is a kind of a checkpoint that our calculations and assumptions are true. So in almost every electrical circuit we are going to solve, we will have an opportunity to have a checkpoint to confirm our solution. So this is electrical resistance in series, R1 and R2. And we mentioned earlier the voltage drop is V1 and V2. And Kirchhoff law stating that the sum of the source voltage around any closed loop, like this loop of a series circuit, is equal to the voltage drop across the resistance in the loop. The sum of the source voltage around any closed loop of series circuit is equal to the voltage drop across the resistance in the loop. Kirchhoff law is known to be series circuit law. So let's apply Kirchhoff law here. E1 plus E2 equal to V1 plus V2. And V1 equal to I1R, R1I, V2 equal to R2I. That means E1 plus E2 equal to R1I plus R2I. That means E1 plus E2 equal to, I will take I as a common, I R1 plus R2. What that means? So R1 plus R2, I could call it the summation of the electrical resistance. R total. So R total equal to, it means R total equal to R1 plus R2. So when I have electrical resistance in series, the total resistance will be equal to the summation of the resistance connected in the series. What if I have many electrical resistance connected in series? The same thing. The R total will equal to the summation of the resistances. Total sum of resistances in series is equal to the mathematical sum of all the individual resistance in series. Easier. So it's very nice to see electrical resistance in series, but this doesn't happen all. What if the resistances are in parallel? Like this electrical circuit, R1, R2, R3. So in this case, the law is a little bit more hard to remember and apply. The total resistance equal to 1 divided by the reverse of the summation of the reverse of each resistance. So R total equal to 1 divided by 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. This law must be memorized. What about I total? I total will equal to I1 plus I2 plus I3. So this is the source current. This is the source voltage, produces this main current. I call it I total as a better expression. It will be divided to I1 and divide it here to I2 plus I3. So I2 will go this branch, and I3 will go to this branch or to this resistance. So I total equal to I1 plus I2 plus I3. We must memorize this resistance in parallel law. Now we will go to the most interesting part for me and for you, which is we will take an example. We will start example 1 and 2 are easy, and then examples number 3 will be more require more work from us to solve. Examples, chapter 4. Example number 1 is a series circuit. Consists of 3 resistances, R1, R2, R3, and 3 voltage source, E1, E2, and E3. Our mission is to find the current and the direction of the current. The value of the E1 is 10 voltage, E2 is 20 volts, and E3 is 10 volts. R1 and R2, R3 are given values, 1 ohm, 3 ohms, and 4 ohms. So there is a way I like to follow for solving that kind of problems, which is making a table like this table. And on the row, we will put the ohm, ampere, and voltage. And in the vertical, we'll put all the loads, R1, R2, R3, and R total. R total is the summation of these 3 circuits, 3 electrical resistance in series. Okay, what we know here, we are going to put. So what the information available? What are the information available? The resistance value. So R1 is 1 ohm, R2 is 3, and R4 is 4 ohms. Okay, then they are connected in series. So I know now R total. R total how much? The summation. 1 plus 3 plus 4 is 8 ohms. Now, next I will put the voltage total, the source voltage total. So where is my direction for this circuit? I'm assuming the direction is following this direction. Okay, so E1 is in my direction, E2 in my direction. So the voltage, the source voltage total is equal to E1 plus E2. Then I go here to E3, it is in the opposite direction, so minus E3. So 10 plus 20 minus 10, so 20 volts. This 20 voltage is the voltage here for the R total. Okay, now what ohm law tells me? I equal to V divided by R. So this I will equal to 20 divided by 8 equal to how much? 2.5 amperes. Okay, good. So I will write here I equal to 2.5 amperes. The 3 electrical resistance are in series. So the current passing through all of them are the same current, 2.5 amps. Now, how much V? V equal to Ohm's law, R, I, or IR. So 1 times 2.5, 2.5, 7.5, 3, which is 3 times 2.5. And then the last one is 4 times 2.5, which is 10. So what is this? This is simply the voltage drop across each resistance. This is a checkpoint. We need to have some checkpoint to confirm that we are doing good. So the voltage drop here plus the voltage drop here plus the voltage drop here equal to the source voltage. So these values, sum is 20. Ah, correct. So we are doing right. Problem solved. So we go to the example number 2 for parallel circuit. Yeah. Example number 1 was easy, correct? Okay, let's go to example number 2. So these are our circuits. 3 resistance in parallel and 2 electrical source for voltage E1 and E2. We were given the values for the E1 and E2 and the values of the resistance, and we were requested to find the current I total. And we will find also I1 and I2 and I3. So again, we do the same table, same arrangement. And we put on the columns the resistance R1, R2, R3, and R total. We put the values which we know, which is R1, R2, and R3, 10, 15, and 40 ohms respectively. And we calculate the total electrical source in this closed loop, or this closed loop, or this closed loop. So since the current assumed in this direction, so it will be equal to E1 plus E2. So E1 plus E2 equal to 50 volts. Okay, so we do remember that from Kirchhoff law that E1 plus E2 equal to I1 R1 equal to E2 R2 equal to I3 R3. In another word, the voltage drop across R1 is the same as voltage drop across R2, the same voltage drop across R3 equal to the voltage source. That's why we wrote 50, 50, 50, 50. Now I can find the current because V equal to IR. So I equal to V divided by R. So let's calculate it. I equal to V divided by R. So how much I here? 10 divided by 50 divided by 10, 5. Then 50 divided by 15, 3.333. 50 divided by 40, 1.25. And what will be the total current? Total current, I total equal to I1 plus I2 plus I3. So 9.58333. How much R total here? So I know the voltage, I know the current, I can get the R resistance. Resistance equal to voltage divided by the current. So it will be equal to 5.2174. Okay, let's have a checkpoint to be sure that are we doing right or wrong. We remember this is a resistance in parallel. However, we did not use this law, but we can use it to confirm our solution. So R total, let's calculate it. Equal to 1 divided by reverse of R1 plus reverse of R2 plus reverse of R3 equal to these values in front of you, 1 divided by 1 over 10 plus 1 over 15 plus 1 over 40. So if we use our calculator, we'll find out the value is 5.217, which is the same value here. So our solution is correct. Let's take example number 3. Example number 3 is parallel series circuit combination. Interesting, correct? Okay, I encourage everyone to stop the video here and try to solve this question, this example by yourself, and see where you will reach. Okay, so I'm going to solve it with you. So these two resistors, for simplification, we can simplify them. They are two resistors connected in parallel. So simply we can get the equivalent for them, which will be equal to apply the resistance in parallel law. So 1 divided by 1 over 20 plus 1 over 20. So our total will be, so as we do remember, these two values are the same. So it will become 1 plus 1. So 1 plus 1 is 2 divided by 20. So R total equal to 10 ohms. Why? Because the 20 will go upside, so 20 divided by 2 is 10 ohms. Now we have now a new circuit, simplified circuit, where we remove this two resistance by one resistance of 10 ohms. This is our circuit. This is the current law. So let's start with this current law. So this current is I1, is going in this direction, and the current passing will be divided to this current, I2, and the other current will be I1 minus I2. Okay. So this current will be, a new current will go in this direction called the I3. So this current will be equal to how much? I1, this current, I1 minus I2 minus I3. Because the I1 minus I2 divided into this current and this current. Again, this point having two current in I2 and this current, I1 minus I2 plus minus I3. So the summation of I2 and this current, I2 will go with I2, will equal to I1 minus I3. Okay, this is the circuit. Here, this is a checkpoint for us. So here we are having I3, and here we are having I1 minus I3. So I3 plus I1 minus I3, I3 will go with I3, so it's I1. Oh, so it's correct. Let's apply Kirchhoff law. Right, let's take the loop A, B, C, E, F, A. A, B, C, E, F, A. Let's highlight this circuit by yellow color. So it's A, B, C, E, F, A. Okay? Okay, good. So what is the source voltage in this circuit? The source voltage are only this source voltage, and it is in my direction. So 30 volt equal to I1 times this ohm, which is 5 ohms. So 5 I1, then 10 I1 minus 10 I2. So this ohm times this current. I go again with here. Then this current times 5. So plus 5 I1 minus 5 I2 minus 5 I3. I continue. So the current now is I1 minus I3. So I1 minus I3 is, so it is 10 I1 minus 10 I3. Okay, so please, again, let's go through this one. So this loop here, the source voltage is 30 volt equal to I1 times 5. So 5 I1 plus 10 I1 minus 10 I2 plus 5 I1 minus 5 I2 minus 5 I3 plus 10 I1 minus 10 I3. Correct. Now let's simplify our equation. So to simplify it, it's very easy. We calculate first how many I1 we have. So we have 5 plus 10 is 15 plus 5 is 20 plus 10 is 30. So 30 I1. What about I2? We have minus 10. We have minus 5, so minus 15. So minus 15 I2. What about I3? We are having minus 5 I3, minus 10 I3, so minus 15 I3. So let's divide by 15. So divide by 15. So 2 I1 minus I2 minus I3. This equation number 1. Okay, good. Let's take another loop. So let's take the loop A, B, C, E, G, A. So we will take this external loop. So let's mark it with yellow, with another kind of highlighter, another color. Let's mark it with green highlighter. So again, it is, we mark it from A, so A, B, C, E, C, G, and A. This green color circuit. So this is a closed loop circuit. So what is the source voltage here? The source voltage here, this is my direction. So it is 30 volt minus 60 volt, correct? Because it's the opposite direction. Equal to the current times the resistance. So 5I1 plus 10I1 minus 10I2. This is I3 plus 10I3. Okay, let's simplify the equation. So 30 minus 60 is minus 30. I1 is 5 plus 10 is 15. So 15 I1. I2 is minus 10. So minus 10 I2. I3 is plus 10. So let's divide by 5. So 6 minus 6 equal to 3 I1 minus 2 I2 plus 2 I3. Equation. Now let's talk another law. So now I have how many equations before I continue? We have 2 equations. How many unknowns we have? We have I1, I2, I3. So we need three equations to solve the 3 unknowns, I1 and I2, I3. Now I have only 2. I applied on 2 circuits, the yellow color and the green color. So now I have to go to another loop. So here we will take the loop A, B, F, A. A, B, F, A, this small loop. Let's use another highlight. Let's choose something like pink color. So A, the colors will interfere. So A, B, F, and A. Okay, this pink color. So again, what is the source voltage here? 30 volt. Okay, 30 volt will equal to 5 I1, yes, plus 10 I2, plus 10 I1 minus 10 I3. Correct? Correct. Let's simplify. So finally, we get equation number 3. 6 equal to 3 I1 plus 2 I2 minus 2 I3. Now I have 3 equations with 3 unknown. Just a matter of solving the 3 equation for 3 unknown. Then we know already the current passing each resistance. So I am going to write the 3 equations in this new page. These are the 3 same equation, no change. How we solve it? So if we notice here, equations 3 and 2 are similar. So if I sum them together, I'm going to reduce the number of unknowns in the new generated equation because I2 will be removed. So equation 2 plus equation 3, 6 minus 6 plus 6 is 0, then equal to 3 plus 3 is 6 I1, and I2 will be deleted, and I3 also will be deleted. So by this one, I know that I1 equal to 0 ampere. Great. Now, let's put this value in equation number 1. So that means 2 equal to, this becomes 0, minus I2 minus I3. I will call this one equation 4. Let's put the value of I1 in equation number 3. So it will give me a new equation called 6 equal to, so this becomes 0, 2I2 minus 2I3. I will call this one equation 5. Now, equation 4 and 5, if I solve them together, problem solved. So how we can solve them together? What if multiply equation 2 by 2, and then we summation to equation 5? So this, why I'm saying this, because this is minus I2, this plus I2, minus I2, and this is plus 2I2. So if I multiply this equation number 4 by 2 and sum it to equation number 5, they will delete each other, the I2. Then I have only I3, and I can find the value of I3. So equation number 4 times 2 plus equation number 5. So that means 6 plus 2 is 10. So 10 equal to 2I2 minus 2I2 will delete each other, minus 2I3 minus 2I3, so minus 4I3 equal to minus 4I3. So I3 equal to 10 minus 10 divided by 4 equal to minus 2.5 amps. What's the meaning of the minus here? Minus here, it means the current I3 direction is not in this direct current, it's actually in the other direction, which is a logic because the voltage source here is higher than here. So basically the driver current will be in this direction. So it's logic. But we don't need to understand or go through this logic very much because it's clear here from the equation. Now we have already found I1 and I3. We can substitute in any equations and we can find I2. So if we substitute in equation number 1, the values of I1 and I3, we will find that 2 equal to I1 is 0 minus I2 plus I3 is, so minus minus is plus, so plus 2.5. So we can find that I2 equal to 0.5 amperes. Now, this is our circuit. This is the value of the current we found. Let's now substitute these values in this circuit. Okay, so I1 by 0, so I can write here 0 amps. Okay, I2 by 0.5 amperes, so I can write here I2 0.5 ampere. Then I1 minus I2, so 0 minus 0.5, so 0.5, and the direction will be this direction. So 0.5 ampere, but it is in this direction, as illustrated here. Okay, let's continue our process. I3 will be in the opposite direction, and it is 2.5 amps. This is what this current is I1 minus I3, so minus I3 is 2.5 amperes. Now, let's make checkpoint. We need to confirm that our solution is correct. So let's talk another law, this yellow highlighted law, E, C, B, F, A, and again E. So it's this direction. So 60 and equal to 2.5 times 10 plus 0.5 times 10 plus 0.5 times 10 plus 2.5 times 10. Is it true? Let's see. So 2.5 times 10 is 25. 0.5 times 10 is 5. 0.5 times 10 is 5. 2.5 times 10 is 25. So 25 and 25, 50. 50 and 10 is 60. Oh, correct. So this is a checkpoint. Confirm is that our solution is correct. We can take also another loop, just only for the fun. This loop, E, C, P, F. So what is the source voltage here is 0. So 0 equal to 0.5 times 10 plus 0.5 times 10 minus 2 times 5. Yeah, correct, 0. So we are right. Good. So our original circuit was in that way. So how much the ampere in each branch? Simply, it will be half the value of 2.5. Why it's a half? Because the voltage drop between here across this resistance is the same voltage drop across this resistance because they are in parallel. And the resistance is the same value, so the current must be the same. So the current is the same, and the total value of the current 2.5. So it means the current will be divided into half here and half here. So 1.25 and 1.25 ampere. This is the end of our course. Thank you very much. And I understand this is a video, but during the original course, we had asked our participants to ask questions related to the course, and we were answered the question of the participants. So please go to our website, LinkedRings.com, or email to us at info@linkedrings.com, because we are having part number 2 coming very soon, maybe within a week. It means it could be before the end of November, I believe, or maybe the first week of November. I think it will be before the end of November. So I encourage you, please go to our website and subscribe for part number 2. Thank you very much for watching the video up to this point. We appreciate it. Bye-bye.